Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Filip Samuelsson with us today. Hey, Filip.
Hi, Frank.
Where are you located at?
I am currently in Stockholm in Sweden.
Ah, okay.
Yes, in my kitchen, where I work.
Your kitchen looks very Earth-like.
Right, yes. Well, this is the background. Yeah, I know, right?
You can
Couldn't believe Stockholm looked like this, but it does.
You can get some international cuisine that way, I imagine, fairly easily, given that kitchen.
Exactly. No, this is the background I chose, so you don't have to watch my kitchen in the background.
Ah, very good.
So, yeah.
Very good. So what's your position there? Are you a grad student, a postdoc?
No, I'm just a PhD student in my fourth year. So this paper we shall discuss today is my second paper, actually. And it's a continuation of the first paper I published.
Do you have a graduation date set yet?
Not really. I think it's somewhere like I'm a year from it, I think, roughly.
Okay. You're getting close.
Yes, quite close. Yes.
So are people going to their offices in Stockholm, or are you mainly working from your home office, or what's the
so everyone that doesn't need to go into office are not allowed to go. So people doing laboratory work can be there, and people that has teaching that cannot be done via Zoom or any other medium, they are allowed to go in, but I am not. So I've been standing here atop in my kitchen for a year, I think.
I hope you sit once.
Almost. Which I mean that's fine, of course. It's a small price to pay, but it's boring. Yeah, but hopefully we're out of it soon, maybe.
Hopefully this coming year, the world will be flooded with a suitable vaccine, and things will begin to have a significant uptick. So cross fingers.
That would be nice.
So Filip, what do you like to do for research?
Right, so I have done ultra-high energy cosmic ray research. Basically, me and my supervisor mostly work on GRBs in general, gamma ray bursts, which is the topic of the paper as well, but it's focused on ultra-high energy cosmic rays. But currently I'm working on the radiation processes in gamma ray bursts. Okay. So we will hopefully have a paper out on this soon as well. So it's a bit of a switch up topic for me, but it's fun.
Very nice, very nice. Speaking of, this will lead us to this really lovely APJ article, Constraining Low Luminosity Gamma Ray Bursts as Ultra-High Energy Cosmic Ray Sources using GRB 060218 as a proxy. And Filip, take us away.
Thanks. So first of all, you couldn't really guess that, but I'm a fan of short titles. But it's very hard. It's very hard to get low luminosity gamma ray burst and ultra high energy cosmic ray sources into the title without it being very. So it's quite long. Right. So what we do is, so I've watched a few of the interviews that you've had, and I think that they're quite diverse. I will do a very short introduction first on what we're actually doing.
Okay.
So it's all about these ultra high energy cosmic rays. So cosmic rays are charged particles that we discover they're from beyond our solar system. And the ultra high energy ones are the highest energy tail of the cosmic ray spectrum. So you're basically from a few times 10 to the 18 electron volts all the way up and beyond 10 to the 20 electron volts. So this is really macroscopic energies contained in a single particle or nucleus.
Yeah.
And the problem is, of course, that they're charged, so they're bent in the galactic field, so they don't point back to where they came from. So we don't know where they're coming from. We don't know the sources that are accelerating them.
Mm-hmm.
And so the hypothesis basically of this paper is that low luminosity gamma ray bursts are a very favorable source. So gamma ray bursts are these very luminous jetted outflows that we've looked at for a long time, and they've been very good candidate sources, but it turns out a few years back that they don't seem to be that promising anymore. They have a few caveats, strong caveats.
Okay.
One of which that we pointed out in the previous paper. So this is a continuation of that paper then. And two other caveats that the low luminosity gamma ray bursts don't have, which is that when you go to the highest energy end of the cosmic ray spectrum, the composition changes. So from being basically purely protons, it goes to heavier elements.
Right.
Like oxygen, silicon, and iron. And you don't expect to have this in a gamma ray burst jet because it's so luminous that these particles are basically disintegrated at the base of the jet. So you don't get them further out where the acceleration should occur.
Okay.
But in low luminosity, you don't have this problem because the luminosity is, of course, lower. So you could have heavier elements further out. And secondly, you have IceCube has put very strong constraints on the neutrinos coming from gamma ray bursts. And neutrinos is a natural byproduct from very high energy cosmic rays. So you would expect to see neutrinos as well, but IceCube has said that they see basically none from gamma ray bursts so far, or at least the ones that they see don't seem to come from gamma ray bursts. But again, the low luminosity ones could give a sufficient flux of neutrinos without being electromagnetically visible because of their low luminosity. So that's why they are a promising source.
Okay.
So as the name suggests, low luminosity gamma ray bursts are basically your typical gamma ray burst, but they have much lower luminosities. So far, we've only detected very few of these. So basically around 10 or a handful, something like this.
Yeah.
And we're not even sure if they're the same type of class of transient or if it's a different type of transient. Indeed, it probably is different when you compare the rates of the two events, but it doesn't really matter. Now, what we do here is that we look at one specific of these, which is called 060218, because this one has by far the best data available. So it has radio all the way up to very high energies. And we look at this using the data of this burst, and we want to constrain the whole population. So this is, of course, not trivial that you can actually do this.
Right.
So we spend a good portion of the paper arguing why it should be fine in this case, because the things that we look at specifically, this GRB looks to be very typical of the population. But it should be mentioned that as more detections come on, we have to reevaluate to see that the properties actually do match that of the population, so to say. Else, this paper should really be viewed as valid for this specific GRB and not the whole low luminosity population.
Fair enough.
Right, so that maybe was a bit long of an introduction, but
It'll be good. Perfectly good.
So the idea behind the paper is pretty simple, and it's the similar one that we had in the previous paper, and it's that if we want to accelerate particles to ultra high energies, this puts constraints on the source. Specifically, the magnetic fields need to be quite high to accelerate the particles. Now, you would expect electrons to also be there. So you have charge neutrality, and these electrons will, of course, radiate in this magnetic field.
Sure.
So what we do is that we calculate the emission from the electrons, and we compare this to observations to see if it's compatible.
Okay. Yes.
Which basically brings me to the first, well, we can stop at section 2 first. Because that's when we introduce this specific GRB, and it's a few things that I would like to mention there.
Sure.
One of which is given in equation 1, or not specifically equation 1, but what I want to mention for people that are not familiar with this is that low luminosity gamma ray bursts have much slower outflows than your typical high luminosity gamma ray burst.
Okay.
So standard gamma ray bursts have outflow bulk Lorentz factors in the orders of hundreds. So roughly 300, something like this. But low luminosity gamma ray bursts, these are basically mildly relativistic. So you would expect gamma to be of the order a few.
Right.
And this upper limit that we derive here is basically 16. But as argued by several of the authors given in the bottom of this page, it's probably less than 10 in this burst.
Mm-hmm.
But it's not, as with many things, it's not really clear. So to be on the safe side, we actually look at values of the outflow Lorentz factor 3, 10, and 30 in the paper.
Okay.
But I think that 30 is probably, that's quite high.
Upper bound.
Yes, exactly. So that's one thing about the GRB. And then if you scroll down to equation 2, which will become important later on, we have the energy requirement. So basically, yes, there you go. Sorry, there might be a bit of a delay, so I don't see
there's a little bit of a lag. It's all good.
Okay. So in equation 2, what we basically do is that we put a minimum energy that needs to be in this gamma ray burst. And we do this because from Earth, the observatories on Earth obviously discover ultra energy cosmic rays, and they do so with a certain flux. So given that we know that they observe ultra energy cosmic rays with a certain energy, we can infer how much energy these sources need to output if they are the main contributors of these particles. Now, secondly, we know roughly, not very good because we haven't discovered many, but we have an indication of the rates that these things go off. And so we can infer how much energy each event needs to produce in ultra energy cosmic rays. And this gives us a minimum energy that the burst needs to have, basically. And so equation 2 says that given these conditions, we need at least 10 to the 51 ergs in this burst. And this is really the minimum because we've been very conservative with the numbers that go into this. So we've taken everything on their like optimistic side of the uncertainty range. So you need 10 to the 51 ergs, which is higher than what previous people have thought about this burst. But if it doesn't have this energy, then we're done right away, because then if we take this as a proxy, then they can't be the main contributors. So this is what we work with.
Good. Okay.
And then now we can get to figure 1.
Okay, I'm with you. Okay, figure 1. I'm gonna decrease size a little bit to get them all on there. Full column plot. There we go.
Yes. So what we're viewing here, well, first of all, gamma ray bursts are often divided into 2 parts. You have the prompt emission, which is giving you the high energy gamma rays, which is why it's called gamma ray burst. And then once the medium runs in, the jet runs into the external medium, it will start to decelerate, and this will also generate an energy dissipation that will accelerate particles as well. And this will create what is known as the afterglow emission. And we want to look at acceleration both in the prompt emission and the afterglow phase.
Okay.
So here, this section is devoted to the prompt phase. So we will first discuss the prompt phase, and then we will look at the afterglow phase. And they have a slightly different type of method that we use.
Yep.
So what we have in figure 1 here for the prompt phase is the limit on the magnetic field that you need to be able to accelerate cosmic rays. Basically, I don't think that the equations themselves are really necessary to look at, but what we do is that you take the typical timescale it takes to accelerate cosmic rays. It takes a certain amount of time, and this time is dependent on the magnetic field strength. So you look at that timescale and you compare it to typical energy loss timescales that the particles have, and they lose energy through synchrotron emission. They lose energy because the ejecta is expanding, so adiabatic losses.
Yep.
And they lose energy because of the photohadronic interaction, so it will collide with the photon field, losing energy this way. And from this, you can actually use that the timescale of acceleration needs to be shorter than the energy loss timescales, and you convert this into limits on the magnetic field. So from top to bottom, you have these 3 different outflow Lorentz factors that I spoke about. So it's gamma 3 in the top, and it's gamma 10 in the middle, and then it's gamma 30 in the bottom.
Okay, I'm with you.
So I guess we can just zoom in at the middle one of them, so we can see more detail.
Let's look
because they're quite similar. So basically what we see, I should also mention that this vertical dashed line, this is the photosphere below which the ejecta is optically thick. So it's not really relevant here.
Got it.
So the color gradient here is giving you the observed cosmic ray energy so the maximum energy that you could get from the source, observed maximum energy as a function of the radius and magnetic field. So radius from the progenitor. And you can see that the numbered here is the log energy. So if you want to get 10 to the 20 electrovolts, which we have seen, you need to be in this yellowish triangle. Exactly, the one that you're marking. So this is, well, it's not huge, but it's a quite large parameter space. And this is one of the reasons why GRBs have been favored, that only considering the timescales, it seems to be quite all right. You could get this to work with normal values for the magnetic field. So what we do is then, of course, that we take it a step further. We say, okay, but we know the magnetic field strength necessary. What does this mean for the emission of the electrons? So this takes us to figure 2.
Let me ask one question.
Yeah, sure.
Got, I imagine they're different emission mechanisms, but you've got solid lines, dashed dot lines, dotted lines.
Exactly, yeah. So basically the 3 different type of line coding here corresponds to which of the energy loss timescales are dominant.
Right.
So the top dotted lines, these are your upper limits on the magnetic field, and this comes from synchrotron losses. Okay. Mm-hmm. So basically a higher magnetic field accelerates your particles faster, but the proportionality of synchrotron losses is even higher with a higher magnetic field. So the energy losses from synchrotron will become more and more efficient the higher magnetic field you get. So this gives an upper bound. And then the dotted dash is from the adiabatic bound. Adiabatic losses, and photohadronic is closer to the progenitor, where the photon field is more dense. So these are the 3 line codes that we see.
Cool, thanks.
Thanks. No, thank you.
Okay, and
so now we can jump to, we should stop on the way. There is, I think, equation 3 there, which I see, and I don't, yes, exactly. Yeah. So here, the whole thing now is that we know the magnetic field, and we want to calculate the emission from the electrons. So the electrons will radiate synchrotron emission, and this synchrotron emission is well characterized theoretically. It's basically a bunch of power laws that have some characteristic energies. So there are some frequencies which have power law slopes in between them, and the slopes, the indices of the slopes are known. So what you need to do is that you need to calculate these frequencies. And the reason why I'm stopping here is because there are 2 interesting parameters that we will vary later on to see that the results are robust to changes of the parameters.
Good.
And it's basically what you see here in nu m. So nu m corresponds to, so what we assume, which should also be mentioned, we assume that the electrons at the acceleration site are accelerated into a power law, instantaneously accelerated into a power law. So this is a normal, usual assumption that you make. And they are injected into the power law with a minimum Lorentz factor. Mm-hmm. And nu m is the emission from the electrons that have this minimum Lorentz factor. This is what nu m is. And it's dependent on the outflow bulk Lorentz factor of the magnetic field. But the 2 parameters that I want to mention is this epsilon E non-thermal, NT, and psi A. So epsilon E non-thermal, this is the fraction of energy given to non-thermal electrons.
Mm-hmm. Okay.
So we put this to 10% here in this example. And then psi A is the number fraction of accelerated electrons. So how many electrons are actually accelerated? This is very commonly put to 1. That you just assume that all of the electrons are accelerated.
Okay.
But this is not necessarily the case.
Sure. Yep.
Specifically, if you have slow shocks, you can actually show that psi A can't be 1. It has to be small. And so in this example, we have it to 10 to the minus 2. So just 1% of the electrons. So these 2 are not really known, and we shall look at how the results vary with these 2 parameters later on.
Cool.
Right. So that's why I wanted to mention them when we pass. But now we can go to figure 2.
Okay. Nice table there, values, and figure 2. Synchrotron fluxes.
Exactly. So what we have now is that we've known the magnetic field. This was shown in figure 1.
Mm-hmm. Yep.
And the synchrotron flux is a function of the magnetic field. So we can take the constraints that we have on the magnetic field and we can translate them into constraints on the fluxes. And because the shape of the entire electromagnetic band is known from the shape of the synchrotron spectrum, we can compare the fluxes in any band. So what we do here is that from top to bottom, again, is the outflow Lorentz factor, 3, 10, and 30.
Yep.
And from left to right is different electromagnetic bands that we compare to observations. So on the left, which turns out to be the most constraining band, is optical. So we basically, what we've done is that we've calculated the emission and then we've normalized it to the observational value. So the red dashed line here was just 1 now because it's been normalized, but it is the observational value. So if you had all the parts of the parameter space that crosses this is consistent. So if it's lower, then it's fine. It doesn't outshine the emission.
Sure.
And if it's higher, it's the electrons sitting in this magnetic field would emit more energy than we saw from the burst. And so what you can see here in the panel that you've zoomed in is that all of the available parameter space is way above this line.
Mm-hmm. Mm-hmm.
Which means that the electrons would outshine the optical by orders of magnitude. And
yes,
basically the physical intuition is that because the magnetic field needs to be high to accelerate your cosmic rays, the electrons lose energy extremely rapidly and leading to a very high flux.
Okay. Which
is much higher than what we observe.
Yep. One question said that the black vertical line was the photosphere.
Exactly.
But we have a new vertical line here, or at least I didn't notice it before.
Yes.
Purple one? What
so
is
this is a very important line because it shows where one assumption that we made in paper 1 breaks down for this GRB.
Okay.
So basically what it shows is that above this line, our calculated flux will start to deviate from the true flux. And the reason is that we will overestimate the number of electrons that can be in the source.
Mm-hmm. Mm-hmm.
And we didn't have this problem in paper 1 because in paper 1, we never put the total amount of energy to be fixed. But here we have a fixed energy. So the number of electrons can exceed that total energy. And this happens at the blue dash. So everything to the right of the blue dash line should be ignored.
Correct.
And for the panel that you've zoomed in here, it's probably not a big problem because it's so far to the right. But if you look at the lower Lorentz factors, it does affect because it's shifted to the left here.
Correct. Boom, boom, and then on this one disappeared by the time you get to 30.
Exactly, but we motivate this in the paper as well because this part of the parameter space will naturally be constrained by the analysis that we have for the afterglow phase. So that's why we can say that we rule out that part of the parameter space, even if it's not valid in this specific in the method that we use here.
Okay, that's optical.
Yes, this is X-rays. So this is basically where the peak of the spectrum was. So you can see that it's ruled out here as well. It's not as limiting because if you go very far out, you can see that you can start this 10 to the 20, 10 to the 19 starts creeping down almost to the observational values.
Mm-hmm.
But if you look at exactly the red dashed line, I mean, you still overshoot this by a factor of 5-ish. No, maybe a bit less in the furthest down. But it doesn't really matter because if you go to the furthest right, what we showed there is the maximum of the optical and the X-rays. Because for the magnetic field to be possible, the magnetic field value to be possible, you of course need to be consistent with both the optical and the X-ray. It doesn't help that you're consistent with one of them. If you overshoot any of them, it doesn't work.
Mm-hmm.
And so you can see when you take both of them into account, there is no parameter space left.
Okay.
So all of this is to say that the magnetic field cannot have been high enough to accelerate cosmic rays. This is what this figure shows, because then the emission would have been much higher.
Okay.
Having said this, we can take a look at figure 3, because that's when we check the robustness of this result. That's when we vary the parameters. So this is what we called our fiducial parameters, which is what we gave in table 1, which is the parameters we think are most likely or most commonly used. But we want to check if it's robust.
Okay.
So what we do in figure 3 now So now it's instead from left to right, the three different Lorentz factors. So left is gamma 3, gamma 10, and then gamma 30 on the right.
Okay.
So here we use what we call our optimistic parameters, which is that we take the parameters that influence the results the most and put it to the values where they're most easily get cosmic ray acceleration without overshooting the fluxes.
Okay.
So what in practice we've done is that there is this acceleration efficiency that I haven't mentioned, but it enters into the time scale of acceleration. And this is a eta, it's given in the figure text somewhere. And we put this to 1, which means that it's the most efficient acceleration that you can have.
Okay.
And this is probably not the true value. It seems to be around 0.1. This is what's suggested by PIC simulations and theory, but we don't really know. So we put this to 1. That's the most optimistic it can get.
Yep.
We put the fraction of energy given to non-thermal electrons to be 5 times 10 to the minus 4. So this is very low. But there are PIC simulations specifically of slower shocks that it could actually be this low. So we put it, you give very little energy to the electrons now. And then we put this number fraction, how many electrons are actually accelerated. This is now a free parameter. So this is what's given on the x-axis. So we try it for a bunch of different types of number fractions accelerated. And then we just take the maximum cosmic ray energy you can get that is still consistent with both optical and X-rays.
Okay.
And this is shown here.
Okay, I'm with you.
Yes, so basically what we have is that on the right, you can see that when the Lorentz factor is 30, then this parameter space actually starts opening up. So now you can, in parts of the parameter space, get this 10 to the 20 electron volts. There is a tiny region to the furthest right at high radius, which is quite fine-tuned, where you could get it. But most prominently, you could, if you lowered the number of accelerated electrons so that there are actually very few, roughly 10 to the minus 3 or less, then we cannot constrain this anymore when the Lorentz factor is this high. So this is what is shown here. In our optimistic parameters, if you accelerate very few electrons, and if the bulk Lorentz factor was very high, much higher than we think that it actually was, then you could have accelerated cosmic rays in this event.
Okay. Okay. Good.
However, the other two is that even in this most optimistic scenario, if the Lorentz factor is 10 or less, which is what we think it was, you don't get to 10 to the 20 electron volts, even with this optimistic parameters. And it doesn't help that you decrease the number of fraction of accelerated electrons down to 10 to the minus 4.
Yeah. No.
The orange here, before you ask, because I guess you were about to ask.
Well, you read me well.
Exactly. No, but you have the orange and a pink line that appear.
Correct.
So these are that several authors have tried to fit the cosmic ray spectrum using detailed numerical codes where they accelerate the cosmic rays and they propagate it, and then they look at the data to see what they get, if they can actually fit the spectrum. And the orange is that the authors that are in the table or in the figure text here, Heinze et al., they found that you could fit the cosmic ray spectrum even if the highest energy was less than 10 to the 20. So we see some events that are 10 to the 20 and beyond, but these could be the cutoff of the spectrum. So they found that you could fit this with 4 times 10 to the 19 electron volts. So this is what is shown here, that you could actually have a lower maximum energy and it would still work. And the pink is basically a similar type of analysis done by Ab et al., which is the Pierre Aucher team a few years earlier.
Yep.
Slightly different, but yeah, it's basically a similar type of analysis, but they found it to be slightly higher than 10 to the 20. So we show both of these here.
Okay.
Yes.
I'm with you. Very good.
Yes, I think I explained it all right here. Yes, so this is what is shown here, that for the most optimistic parameters, there might be some parts of the parameter space that could work.
Okay.
Right, and then I think we can move on to the afterglow part. I don't think we need to dwell on figure 4. It's basically showing some example spectra of how they could look. And it's figure 4 basically says that for many of these parameters, it peaks in the optical, which is why prompt optical is actually very good diagnostic for this type of research that we did here. So you can see that the peak of the electron spectrum lies in the optical for these values, high values of the magnetic field, and you could. So that's why it's very good. I mean, we would not have been able to constrain this without prompt optical.
Okay.
Right, and then we go to the afterglow phase.
Okay, so now we're in afterglow. Okay.
Yes. So here we use a slightly different scenario. So instead of constraining the magnetic field, what we did was that we used the fact that we need 10 to the 51 ergs to be the main sources of ultra energy cosmic rays. So this is higher than previous authors found for GRB 06028. They roughly found 10 to the 48, 10 to the 50 ergs.
Okay.
However, this was from the assumption that we spoke about earlier. These authors put the number fraction of accelerated electrons to be 100%, so that all of the electrons are accelerated. And this is not really likely. It's probably less.
Yeah.
And if the number fraction is less, it was shown by Eichler and Waxman in 2005, then there is actually a degeneracy in the fraction of electrons accelerated. So the energy could have been higher if you shift some of the parameters, given that only a few percent or something of the electrons were accelerated. So 10 to the 51 ergs is then not unreasonable, even if previous authors did not find this.
Sure, I'm with you.
However, what we do here is that in the Eichler and Waxman paper, they basically say that this, well, if you accelerate 1% of the electrons, there is 99% left that needs to be somewhere. So these have a thermal distribution somewhere. And in the Eichler and Waxman paper, they say that this population could be cool. So they don't get much energy. They sit at lower energies. The emission from them is negligible because they're so cool. However, in recent PIC simulations, all recent PIC simulations that have come up that study this in slow shocks, these electrons actually gain a significant amount of energy, and the power law extends from the thermal population. Okay. Which means that the emission from these electrons is very non-negligible. And this is what we show in this figure. So basically what we have here, I should try to explain this as good as I can, as well as I can. So here we resort to a more demanding numerical code, because now we want to look at both the thermal population of electrons and the non-thermal. Previously, we only cared about the non-thermal because it was sufficient for us to prove the point that we have. But here we need to use both of them. And so we have emission and absorption from both a thermal and non-thermal component. And we have now a supernova that's rising, because this is at 3 days, which means that the supernova is coming from behind, and it helps cool the electrons. And so this code takes all of this into account. But it's also much slower then, of course. So we can't run. Previously, we could check a large parameter space. Here, we can't really do that in the same way. So here are a few typical spectra that we have. All of the solid lines are for 10 to the 51 erg, which is what we need if we want to be a main source of ultra energy cosmic rays. On top of that, we have data points from the GRB. The red data that is at a bump at 10 to the 15 hertz-ish, that's the supernova. So that's the rising supernova that we have.
Got it.
And then around 10 to the 18, 10 to the 16, this is the X-rays. Now, what we want to show with this figure is that if you decrease the number fraction of accelerated electrons, as given in the label, going from black to green,
yes,
you can more or less, I mean, we're not trying to fit it here, but you can become almost consistent with the optical and the X-rays. And the reason is that the high energy emission is dominated by the non-thermal electrons. So if you put fewer electrons in the power law tail, you decrease this emission substantially. However, the huge bump in the spectra that you see at roughly 10 to the 12 hertz, this is the synchrotron emission from the thermal electrons, exactly there, yeah. And this doesn't really change, because if you change the thermal electrons from 90% to 99% to 99.9, they're basically the same. And this overshines the radio data, which you can see from the inset as well. And so it's really important with radio data from the afterglow, because this is exactly where you would suspect the thermal emission to be.
All right.
And
yeah,
and because I've had this question before, so no, I should also mention, so the black dashed line that you have, which is much, much lower, this is when you lower the available energy to 10 to the 49 hertz, which is what previous authors roughly found. And then you're not inconsistent anymore.
Yep.
So it's not a good fit. We tried to tweak it and we got quite a nice fit, but what we wanted to do here was use the exact same parameters that we had for the high energies and just lower the energy to prove that this is the main factor here that makes the difference. So we're not trying to fit the spectrum. We just want to show that it's inconsistent if you have a high energy.
Okay, good.
And also, I should mention that, so some friends of mine, when I showed this, they said, well, it's almost consistent. Like if you just shift the spectrum a bit to the right, you would be consistent. But I want to point out first that the x-axis is 18 orders of magnitude. So it's a huge energy span that's being plotted here.
Yes.
Secondly, from the inset, and also from the light curve, which we don't show here, you can actually show that there's a break at 10 to the 16 hertz. So from the inset, the two data points on the left have a different slope than the two data points on the right. And so there should be a break, and this is definitely not what we see if we have the thermal bump there.
Okay.
And thirdly, this inverted triangle is actually a 3 sigma upper limit that you overshoot here in this plot by, I don't know, 1 order of magnitude, maybe more, a bit more.
Yeah.
So it's not consistent.
Okay.
Right. So it basically shows you can't have that much energy in the afterglow phase. And finally, trying to quantify this, because again, it's dependent on the parameters you choose. So the last figure is figure 6, where we try to, again, we want to see the robustness. We try to vary the parameters that we use to see, can it become consistent if we change some of the variables. Specifically, we want to change epsilon E and epsilon B. So this is the fraction of energy given to magnetic fields, is epsilon B.
Yes.
And epsilon E is the fraction of energy given to electrons. Now, epsilon E is the fraction of energy given to all of your electrons. So previously, it was only to the non-thermal, but here it's to the thermal plus non-thermal. And this is an important distinction, because even if, so PIC simulations have found that this epsilon E non-thermal, how much energy you put in your power law tail of the electron distribution, this can actually be quite low. Specifically in slow shocks, it can be quite low. But these same simulations always find that you still give a quite significant portion of your energy to the electrons when you encompass both the thermal and the non-thermal. And they find that this fraction is 0.1 to 0.2. So this is what is being indicated by the vertical cyan line.
Yes. Right here, yes, okay.
Yes, so you should, according to PIC simulations, you should be roughly there. Now, the different R values is so we've looked at the most constraining radio data point that we had. we ran a bunch of different simulations for different values of epsilon E and epsilon B. And then we looked at how much do you overshoot this radio data point, including the error on the radio data.
Okay.
So at R, the dotted R equals to 1 line. Here you're consistent with the radio.
Yep.
So if you're below this, you do not overshoot the radio. But if you're at R equals to 10, you overshoot the radio data, including its 1 sigma error bar by 1 order of magnitude.
Okay.
And you can see that if you're at the epsilon E values that are suggested by PIC simulations, you overshoot by almost 2 orders of magnitude. Yes. Regardless of your value of epsilon B here.
Mm-hmm. Okay. Yep.
So this is to try to justify that even if you vary these parameters, it doesn't help you unless PIC simulations have, if they don't have the correct values of epsilon E. You need epsilon E to be 10 to the minus 2 at least, or lower for it to be consistent here.
Okay.
Or a simpler explanation might be that the blast wave was not as energetic at 10 to the 51 ergs, in which case you don't have enough energy to be the main contributor of cosmic rays.
Right.
And this is important as well because the blast wave, this constrains the prompt phase as well, because unless you lose a significant amount of your energy, so a majority of your energy in the prompt phase, this will go into your blast wave in the afterglow. So if we can constrain that the blast wave of the afterglow is not as energetic as 10 to the 51 ergs, then likely the prompt phase was not as energetic as 10 to the 51 ergs as well, unless it manages to lose, a majority of its energy. Mm-hmm. So this is an independent constraint on both prompt and afterglow phases.
Okay. Mm-hmm. I'm with you. Cool. Very cool.
Yes, I think that was it. And I didn't time myself, so I have no idea how long that was.
It's all good. It's all good. Very nice. Very nice. And I'm just peeking for myself here. Very cool. All right. Well, that was awesome. So, Filip, where do we go from here over, let's say, the next 5 years or so? Is there new calculations? Is there new observations? Hopefully, maybe we'll discover another 100 low luminosity GRBs.
That would be nice.
So, where do we go from here, given your published article?
So two things. First of all, there is a bunch of interesting experiments coming up, both on the cosmic ray side and on the neutrino side. There are upgrades coming, which would increase the statistics on the cosmic ray side, which is very interesting because now you see this tendency towards heavier nuclei, but it's not really well constrained. And I didn't mention that, but everything that was in the article is for iron. So this is the heaviest you can get. But it's likely less heavy than that, in which case you could get much more constraints on these sources.
So these are upgrades to IceCube?
It's upgrades to IceCube. It's coming along an experiment which is called GRANT, which will measure even higher energy neutrinos. So IceCube measures slightly below, which would correspond roughly to a cosmic ray energy of 10 to the 18. But if you want to probe the really high energies, you need to go a bit higher energy in neutrinos. But then there's also upgrades coming to both Auger and the telescope array, which is going to be nice. That will increase the statistics and also probe more where they're coming from, the cosmic rays, and as well if there are nuclei or what composition is the cosmic ray spectrum.
Yeah,
which is going to be good, I think.
Yeah, that would be great.
Because you need the statistics if you want to do theory.
That you need to know the composition a little better. That will help a lot on what that's going. So that's very cool. So it sounds like there's going to be lots of activity over the next couple of years, which will certainly take you through your defense.
Yes, I hope so.
And it will probably carry on for a few years past that. So that's very cool. Gives you lots of work to do in the future.
Absolutely.
Very
There's always work to do, I think, which is nice.
Very good. All right, Filip, I want to thank you so much for taking the time and sharing your lovely article with us today.
Thank you. It was fun.
Yeah. All right, everyone, thank you so much, and we'll see you on the next one. Bye-bye.
Bye.